Therefore, Bob needs to introduce a new coordinate x prime t prime to describe clock B. If he sets a new coordinate such that the metric tensor on the surface of the moon measured in coordinate x prime t prime equals to the metric tensor on the surface of Earth measured in coordinate xt, that is. So this is the metric tensor at the location of clock B measured in coordinate x prime t prime. It equals to the metric tensor at the location of clock A measured in coordinate xt. So what does this mean? So this is similar as this case. Here we have two rods, A and B, and Alice set one coordinate system xt, in which the length of rod A equal to 10 centimeters and the length of rod B is 5 centimeters. Then Bob set a new coordinate x prime t prime with the coordinate transformation x prime equal to 2x, t prime equal to t. Therefore, in Bob's coordinates x prime, t prime, the length of rod B takes a different value as 10 centimeters. So the length of rod B measured in coordinate x prime, t prime equal to the length of rod A measured in coordinate xt. Here, similar thing happens, but with the length of the two rods replaced by the two metrics. One is a metric on the surface of Earth, and the other one is a metric on the surface of the Moon. Then the Lagrangian density on the surface of the Moon written in coordinate x prime t prime is given by this. Therefore, the two Lagrangians, equation 4 and equation 1. Equation 1 is the Lagrangian density at the location of clock A, written in coordinate xt. They have the same mathematical form due to equation 3. Here, since all the differences between the mathematical forms of the two Lagrangians LA and LB is caused by the difference between the two metrics GA and GB. Therefore, if the two metrics are equal, then the two Lagrangians will have the same mathematical form. Then the period of clock B calculated in coordinate x prime t prime equals to a period of clock A calculated in coordinate xt. That is, these four values now they equal. Therefore, the value of the period calculated from the theory. This is the value calculated from the theory. Matches with the value of the period displayed by the experimental instrument, which is the clock device. So this is the value displayed by a clock. This is the value calculated from theory. Now they match. Suppose we have two identical atomic clocks A and B. Clock A is in Minkowski spacetime, measured in coordinate xt. The metric is given as this. The QED Lagrangian density becomes this. So you can say this is the normal derivative. The Hamiltonian of the hydrogen atom in clock A can be derived from QED physics as this Hamiltonian. And in this reference, you can find some detailed information on how to derive this Hamiltonian from this Lagrangian. And the energy levels calculated from the equation 7 are written like this. So omega 1 is the frequency of the clock. Clock B is put into a spacetime which is not Minkowski, measured in coordinate xt. That is, the QED Lagrangian density inside of clock B measured in coordinate xt is given by this formula. So now you can see here, it becomes a covariant derivative now. All the above quantities are relevant to GB. Then the Hamiltonian of the hydrogen atom in clock B derived from equation 10 will depend on GB. That is, so this Hamiltonian will depend on GB Here, the square sign does not mean they are equal. It just means this Hamiltonian is related with GB. And the energy levels are like this formula. And also, this energy level will be related with GB. Therefore, two frequencies of the two clocks are not the same. However, Bob can introduce a new coordinate, x prime, t prime, such that the metric tensor where clock B is located equals to a Minkowski metric tensor where clock A is located. That is, then QED Lagrangian density of clock B written in coordinate x prime, t prime becomes this one. So now you can see this becomes the normal derivative. The Hamiltonian of the hydrogen atom in clock B can be derived from QED physics as this formula. And the energy levels are like this. So this is exactly the same with equation 8, which is the energy level of hydrogen atom inside of clock A. The two clocks will have the same period value. So what is the motivation of doing this? Because our task is to find a coordinate x prime, t prime, in which the metric tensor satisfies this condition. Since all the differences between the mathematical forms of the two Lagrangians, LA and LB, is caused by the difference between the two metrics. If the two metrics are equal, then the two Lagrangians will have the same mathematical form. As a result, the two Hamiltonians of the two hydrogen atoms will have the same mathematical form, since the Hamiltonians are derived from the two Lagrangians. Therefore, the energy levels in two hydrogen atoms will be the same, and the period of the two clocks will also be the same. Then the periods of clock B measured in coordinate x prime, t prime will equal to the period displayed by clock B. The two-dimensional Schwarzschild metric can be given by this formula. Now we consider two observers, Alice, who carries the atomic clock A, and Bob, who carries an identical clock B. We have TDs equal to TBDs. Alice, who sets a coordinate TR, is rest at I approach to infinity, and I is the location of clock A measured in coordinate TR. Suppose the period of clock A calculated in TR matches with the period displayed by clock A. We have TKA equal to TDs A. Bob is rest at RB, and this RB is also measured in Alice coordinate TR. In Alice coordinate TR, the two metric tensors at the two locations are given by these two formulas. Since RA approaches to infinity, therefore, the metric at the location of clock A becomes Minkowski. Since GA does not equal to GB, the two clocks will not have the same period calculated in coordinate TR. That is, the period of clock B calculated in coordinate TR will not equal to the period displayed by clock B. Therefore, Bob needs to set another coordinate T prime R prime, in which the metric tensor at the location of clock B equal to the metric tensor at the location of clock A measured in coordinate TR. That is, so this is the metric at the location clock B, written in coordinate T prime R prime, and now become Minkowski. Therefore, this four will be equal. Then the metric transformation between different coordinate systems can be given by this formula. So this is the metric tensor at a location of clock B, written in coordinate TR. And this is the metric tensor at a location of clock B, written in coordinate T', R'. And this is the transformation between these two metrics. Therefore, we obtain these three equations. If we treat the ticking of clock B as a physical event, these events occur along Bob's co-moving frame T', R'. Since clock B is at rest measured in coordinate TR, we have dr divided by dt equal to 0. Then we obtain partial R', partial t equal to 0. Then we combine these four equations together. Finally, we can obtain the time dilation results given by this. So this is time dilation in gravitational field. It is reproduced. So in summary, pendulum clock vs atomic clock. The period of pendulum clock depends on the value of gravitational acceleration g, and it is well understood as this formula. So this is the period of the pendulum. And from this formula, we can easily calculate the time difference measured by two pendulum clocks on two planets with different gravitational accelerations. And the period of atomic clock depends on the value of metric tensor, g mu v. But the formula is not known so far. We don't have such formula for the atomic clock. But we can introduce a new coordinate and do coordinate transformation between the two coordinates to obtain the time dilation result. So here is the motivation. For the pendulum clocks, we have the formula of the period which carries the factor g. But for the atomic clocks, we did not obtain the formula for the period which carries the factor g mu v. Therefore, we cannot calculate the time difference measured by two identical atomic clocks located at the two places with different g mu v. However, we can do the coordinate transformation to obtain the time difference. This is what we have done to obtain the time dilation measured by the two atomic clocks A and B. First, we set a coordinate t, x, in which the time parameter t matches with the time displayed by clock A. Then we set a new coordinate t', x', in which t' matches with the time displayed by clock B. Therefore, the time difference between the two clocks is just the difference between the two coordinate time parameters, t and t'. This difference can be obtained from the coordinate transformation as given by equation 16. The gravitational acceleration g depends on the changing of the metric tensor. Therefore, the period of a pendulum clock depends on the changing rate of metric tensor. The 16 elements of the metric tensor need to be taken as a constant within the size of the clock. Otherwise, we cannot perform metric transformation, which is equation 16, to calculate the time dilation effect inside of the atomic clock. The clock counts the number of occurrences of one physical phenomenon, and it displays a number TDIS on its screen when this physical phenomenon occurred once. This number TDIS is called the period of the clock, which is fixed by the internal construction of the clock itself. Now we set a coordinate xt to describe the physical phenomena occurring inside the clock, such as the energy levels of hydrogen atom and atomic transitions inside of an atomic clock. Based on this coordinate xt, we can write down the physics formulas of energy levels and calculate out the value of the period of the atomic clock as tk xt. And if we set another coordinate x prime t prime to describe the energy levels of hydrogen atom inside one atomic clock, a new value of the period of the atomic clock can be calculated out as t prime kel. And usually we have these two values does not equal. Therefore, an infinite number of values of tk can be obtained if an infinite number of coordinates are applied, but only the value equal to number TDIs, which is displayed by the clock, is legal. Therefore, we need to choose a coordinate such that the period of the clock calculated in this coordinate equals to the period displayed by the clock.